Welcome everyone to our today's webinar. So this will focus on radar, RF, and TEM applications using COMSOL multiphysics. And we will have a slight outlook to other multiphysics applications. I'm one of the application engineers here in the company. Technically, I cover the finite element modeling suite, which is COMSOL multiphysics. And this is very suitable for various physical modeling and simulation applications to build virtual prototypes. What we are going to see and hear today. So here's our agenda. So different size means maybe different features and physical setups and different predefined physics interfaces. So we will get a walkthrough on the size, how does it affect the different physics interface that we want to use and utilize during car simulations. And since we have multi-scale, so we can use different methods to solve basically the same equation, whether we want to use in a frequency domain, maybe in a time domain, or we could use different ray features, ray detection features, how you can couple different phenomena like the finite element formulation to the boundary element. So we will have a look into it. So there is a demonstration for that. And at the end, we have the Q&A session. So if you don't mind, we can go back to your questions at the very end. So feel free to take notes and we can handle them at the end of the presentation. Okay, so let's jump into. So technically, we will use most of the features that are covered here from the RF module. So it's very capable for various applications. Here you can see some snapshots for patch antenna arrays with the directivity plots, just to name a few. And what we will use is COMSOL multiphysics. You may not be all that familiar with the product, the user interface, the suite itself. So let's have a few slides describing the basic features. How does it look like, where you can find the settings and physical features. So it's, as the name says, it's true multiphysics solution. So we have one user interface for different physical applications. You can start with a single physics and let's say an antenna design, some electromagnetic compatibility analysis, like you can see here on the right-hand side. And then you can add gradually more and more physics to your model. So you can later add structure mechanics and heat transfer. Maybe you want to couple them together. Let's see how the heat affects the performance. Does it need an active cooling or a passive one is suitable? And there are various applications where you can include and involve more than one physics. And since we have a one user interface, so the foundation is built on one language, you don't need to jump back and forth in and out between different user interfaces. You have all the settings, the solutions, all the workflow in one place. That's a really efficient way of working. Then we have the application builder. It's core COMSOL functionality, so you don't need any additional module for that. So you can turn any finite element model into an application and you can share it with others, with customers, within the company, within the department. You can create a snapshot of your model and you can distribute it with others. That's really easy to do that. There are various built-in examples where you can start and how you can start building an application from a finite element model. And then there is also the model manager, which enables you to track and validate models. You can log them, you can add tags, you can search in the model manager directory for physics, for boundary conditions. So it has a very powerful search engine. So you can merge also different branches and you can have a repository for managing your different model versions, different revisions. That's also in the core COMSOL functionality. So that's the model manager we are talking about. Going forward, So here on the left-hand side, you can see the model builder. This is how the product is set up. So you start at the top with setting up the parameters. You can have different parameter nodes. One, for example, for the geometrical properties, one for the material properties, one for load settings, and so on. Then you can set up the geometry. You can use built-in COM source kernel, or you could import from third-party solutions, or you could also use a live link if you want to import a parametric geometry. So you can use any of the live link for CAD products for that purpose. Then you can assign the materials, physics. You can start with a single physics, then you can add the multi-physics node. Then you set up the study nodes depending on your needs, maybe on a time domain. Then you want to switch to frequency domain. Maybe you want to create an FFT from your solution. So there are different techniques tailored for that dedicated physics feature that you are using. At the very end, you can post-process your results at the results node. So that's technically and logically, that's the last part. When we stop, we investigate the results, and we can make conclusions whether we have the right boundary conditions, right mesh settings, and so on and so on. And for talking about and turning our attention to the electromagnetics, that's what we are looking for today. So there are different modules for different purposes, depending on the size of your model, the wavelength, so different prescribed physics interfaces. Basically, and yeah, literally we are solving the same equations independent of the module. Maxwell equation, that's the covariance fundamental equation that we are looking for. So if you are going for low frequency electromagnetics applications like in transformers, motors, just to name a few, then the AC/DC module is the right choice and the right solution. It also includes multiphysics capabilities, predefined multiphysics capabilities like the Joule heating or induction heating. Then if we going to rather to look for the wave propagation in a different frequency regime, then an RF module is the right choice and the right solution. You can calculate, you can use it for simulating antennas, calculating the radar cross-section. It also includes the multiphysics coupling to microwave heating, so that's included with an RF module. And if we are going down to the size, to optical devices, so we are still looking for the wave propagation, but the geometrical size is comparable in the same range, like the wavelength, like for optical beams, and we want to investigate scattering effect, scattering itself, then the wave optics module is the right choice. And it also comes with the laser heating multiphysics capability. And if we are going for optically large geometries like antennas, large cameras, large sensors, spectrometers, then we could use rather the ray optics module. So it has dedicated solutions and features to go with. And it also includes the stop analysis. So you can investigate what happens to the focus, the focal length, if the thermal distribution, the temperature distribution is changing over the camera system. Sometimes it's not neglectable. If you have a camera, a compact camera, DSLR or something like that, and you are taking some photos in the room temperature, but you go outside and it's minus 30 degrees, the camera still has to operate in the same conditions. So you need to take into account the temperature differences also. So there are very, very few physical domains where only one single physics is enough to accurately model your real-world problems. Study types. So we mentioned the different modules that can be used for different purposes. There are different study types. Here you can see some examples from the built-in application library, where you can use the mode analysis for waveguides, for example. You can search for frequency domain or for frequency to time, FFT. There is a very wide range of applications that you can use here, from automotive applications to digital health applications like an MRI or other devices that includes huge magnetic fields, and it can have a huge impact on temperature distribution. You can also use, on top of the time domain and frequency domain, you can use full transient modeling. That's also included. So if you need to take into account the transients and other harmonic generations, that's also included in the modules. So that's possible here also. And as we mentioned earlier, there are very few cases where these applications stand alone with like a single physics model. Most of the times there is some sort of heat generated temperature rise. So that can be included, whether you are dealing with a human head in an MRI application or with RF heating and Joule heating applications. That's also included, and you can couple them together quite easily. And going further, if we have a temperature distribution, then we probably have mechanical stresses. So we can go further and we can add additional physics interfaces. So here later in the demo part and with the patch antenna array, I will do the same. So I will include the model with a heat transfer and structural mechanics physics interface. So that's also included, and you can set up as many physics as you wish. There is no software limitation on the number of different physics you want to include in your model. And the good news is that we have other, let's call general purpose modules, like an optimization module, and that's not tied to any physics or any module. So you can include, and you can use it as an optimization setup, let's say, to create and model maybe a frequency selective filter or any antenna array with a dedicated directivity pattern, just to name a few. So you can include and you can use the built-in functionalities. So there are two options, like the gradient-free optimization. So you can create new geometries during the optimization algorithm, and the big other portion of the family of optimization algorithms is the gradient-based optimization. Since it's based on the gradient, so it needs to calculate some analytic function that can be derived during the optimization algorithm. So it runs faster, so it has different purpose. Depending on your needs, you can choose which version fits your solution, fits your needs better. So you can use also the optimization module. Here you can see a few snapshots. So these are from the application library, just to name a few antennas that are available here. And we can stand and share the slides with you. So don't worry about, of course you can take notes, but we will hand out these to you with all the links available, targeting the application libraries from COSA's website. Domain features, you can mimic and model infinite element domains. Let's call the perfect image layers. So they will absorb all incoming waves, so no reflection will be allowed. And on the outer part, if you want, you can add a perfect electric conductor to absorb all external radiations, like mimicking an echoic chamber. That's also possible. And you can set up a background field excitation. So if you want to, let's say, use the model for scattering and to calculate the radar cross-section. And boundary conditions, there is a very, very long list of boundary conditions that's available for different purposes, but the perfectly electric conductor and some lumped port and excitation, technically in most cases you can start to build your very first antenna with these boundary conditions. And then you can extend with any more, like including external circuit layouts. That's also possible. And there are dedicated features. So if you want to include a layered shell, that's also possible. So you can import several layers of PCBs, for example, and we will touch a few of them during the demo. So here you can see a list of those. It's not the full list, but just a snapshot of which features are available here. Geometries, they can be like thin. Geometries typically, sometimes they are thin, so you can use a boundary condition for that, so you're not tied to creating a 3D geometry. That's also possible, and you can take into account the skin effect. You can calculate the skin depth, and you can investigate maybe the mesh independency on your solution, and that's also possible here. Several material models exist. Here you can see a few of those. You can set up different material constitutive relations depending on your needs and depending on the module you are looking for, whether you are in the low frequency regime or in a high frequency regime. There are different options for different modeling and simulation needs. And then when you arrive at the very last part, the results node, so you want to post-process your results, there are built-in predefined plots. So those are ready-made plots for you, like Smith plot and directivity plot. And you can also use any of the built-in variables to investigate the results of your simulations. You can plot the excitations, whether they are in plane or out of plane. So you can set up very nice visualizations for that. And you can also create touchstone file export. Sometimes it's really useful to investigate further your results and import other solutions. Axisymmetric modeling, sometimes that's the easiest case, but you can do, so it's a really efficient way of modeling, and there's an automatic mesh generation, so it takes into account whether you have a perfectly matched layer or some highly conductive layer. The console will automatically adjust the meshing algorithm based on your boundary conditions. Okay, so let's jump into our first demo section. So this will be a Microsoft patch antenna. So we will start with this. So we will see what different boundary conditions that are we going to apply. And then I will apply some additional physics to that. So we can add the heat transfer and structure phenomena for that. And then we can couple that to boundary element. So we can couple the two methods together, the finite element and the boundary element method. So that's our first demonstration model here. So let's jump to console multiphysics. Let's go back to our full screen section and let's start with different ones. So start here. Okay, start with this one. Okay, so we have a prepared version for that. So the geometry is set up, which is an import. So you can use ComSys kernel, as I mentioned earlier, but you could also use some third-party tools, or you can import the geometry from other ComSys models. So there are several options how you can start your modeling workflow. Then we have the materials assignment. So we have an air, that's the surrounding domain with all the relevant properties. And then we have the substrate. So that's the material assignment here. And then from the physics. So we are using the electromagnetic waves frequency domain physics interface for this purpose. And in every physics interface, here in the equation view, you can always look for the equation that we are looking and that we are going to solve during the simulation. So it's easy to check whether you are in the right physics interface or not. And if you wish, by default it is hidden, but if you wish, then you can override all the discretized equations, all the numerical equations, or if you want to investigate different numerical schemes, for example, that's also possible here, but not today. So here we have some boundary conditions set up, like this lumped port. So we have an excitation here. So we have this little red arrow indicating where the port is. So this is the port we are looking into, and it is a cable type. You can change it to current or circuit if you wish, and it has a voltage excitation of 1 volt. So that's the setup here. And we have far field domain. So we want to calculate the far field radiation pattern. So we add it here to calculate that. And we have some boundary conditions missing. So let's set up those. So we need some electric conductors. So here you can see all the boundary conditions. We have a lot, but most of the cases we can start with PEC, perfect electric conductor. For most of the cases, that's the very first choice to go with designing our antenna. Okay, and we need to select the first one as the patch, so they are predefined. So this is one for the patches, and then we can create another one for the feed network. That will be our second part. So this is the network connecting the patches. Okay, and we need a third one for the ground. Duplicate and select the ground. Okay, so this is another electric conductor. So they are selections. They live here under the selections node. You can see they are so-called explicit selections. So they are explicitly selected and put into these selection lists. So it's easier to select them and group them together once. Then you can just use the drag and drop section and select what you already grouped together. So you don't need to click here manually several times to select specific boundaries. Okay, so we have these setups. And we have an artificial domain. So this is the perfect image layer, which is the outer layer. So the upper half is hidden, and here you can see from the text also, but the lower half is visible, so you can see this little layer. This is the perfect image layer, so it enables the absorption of incoming waves, so there won't be any reflection to our model into our modeling environment. And from the study type, we have a frequency domain for a single frequency for F0, which is, let's check it, it's on 1.68 gigahertz. Okay, so I already have the solution, so let's go to that version. It's easier to open up that than waiting for to be solved. Patch antenna array. Okay, so it's the same. So we have these conductors for the patch, the network, and the ground, like we have seen previously. And then we have the solution already here. So we have the 3D plot of the electric field to check how does it look like, so we can visualize them quite easily. And then we have a 2D far field plot, so we can see how this antenna will behave, what will be the radiation pattern. So it looks like this way. And then we have this plot of a 3D version, so that's also possible to visualize, and it's easier to investigate. So this is how our antenna will behave and how it will radiate through our air domain. So this is the first section here. And then we can add different physics. So here currently we have one physics, electromagnetic waves, but we can add more to investigate further. So we can add physics like heat transfer in solids. or the antenna domains. Okay, so they are technically domain 6 and 7. So we want to calculate the temperature distribution. What will it look like? Then we can add the heat flux to enable the heat to be transferred to the patch. Okay, and to the top surface. And we can set up a convective heat flux with heat transfer coefficient of, let's say, 5. That's typically when there is no external cooling. And that's it technically. And there's a multi-physics node. It appeared automatically since we have more than one physics. So right-click and electromagnetic heating. It enables us to couple the two physics together. Okay, and so the electromagnetic waves and the heat transfer in solids, they are automatically coupled together. So that's easy. How you can add the true multi-physics problem here. So the losses will be transferred to the heat transfer model. Okay, so that's one section here, and we can go further. We can add some other physics, like since we have, or let's suppose we will have some temperature difference, so we can extend the model with the solid mechanics interface for the same domains. So we can here just clear, and we can add manually the two domains where we have interest in. Okay, and then we should, let's say, fix the bottom boundary to enable some rigid constraint there to disable the rigid body motion. So let's go to the very bottom surface. Okay, so that's a fixed boundary, and technically that's it. So no other external mechanical stress will be distributed that will come from the temperature difference. So go back to multi-physics, right-click, thermal expansion. And we can couple the domains together, where of course it's not applicable, that won't be coupled, so it's quite smart to detect which boundaries are relevant for our physics. Okay, and the thermal expansion coefficient is read from the material properties. Okay. You can also include thermoelastic damping. So if it's cyclic deformation, sometimes it's possible, sometimes the effect of this thermoelastic damping is not neglectable, so you can include that one. But in our case, that's not the case here, so we don't really need that one to be included. Okay. And what we also need is a study type. So let's open up the stored model here to investigate further. So let's go back there, and I have a prepared version where it is already stored, multi-stored. So let's jump into that one. So we have set up solid mechanics and the heat transfer in solids interface to couple the effects together. And the question is that what should we do with the time? So we could calculate a transient solution, or we could also calculate a stationary solution. So here the case is that we want to go for the stationary solution. So let's see what will be the stationary deformation and temperature distribution. And about the time stepping, since there is a frequency domain physics interface, this is an antenna, it has some sort of excitation. But for the heat transfer and the solid mechanics, we don't really need a frequency domain solution, rather in the static stationary. So this solution is that we use a built-in predefined node for that, and it's called frequency stationary. So it automatically handles the frequency domain physics interface, the electromagnetic waves interface in the frequency domain part, and calculates the time averaged and frequency domain averaged load to the heat transparent solids interface, and for the heat transparent solid mechanics interface, a stationary solution is created. So we can couple the two fields together with the three different physics. So we have the same electric field, what we have seen previously. Sorry, not this one. Yeah, so we have the same solution here, and we have some sort of temperature distribution. Here we can see how the heat will go and distribute over our antenna array, and then we can have a displacement field here. So it's magnified, and they are in a micrometer range. So we can have deformation of 1, but you can overwrite anywhere and you want if you want. So that's the original deformation. So at the bottom is 0, since we have a fixed boundary condition. At the very top, so we have some sort of deformation, what we can see here. But wherever you can click here in COMSOL, you can technically plot anything you want. So you can plot 1 if you wish, or you can use any of the built-in variables. So here you can find all the built-in properties and variables, but you can add your own. So in the expression field, you can type any expression you are looking for. Then let's put back the displacement field and in micrometers. So that's how you can add different physics to your single physics model and expand. Then we can add the boundary element method. So let's go into our extension here. So we have a boundary element version here. So here we have the same electromagnetic waves. Let's look into it. So we have an antenna. We have the same lamp port. So we have an excitation with the same voltage. PAC, like a typical boundary condition. And the far field domain is pretty much the same boundary conditions. And then we can add the boundary element physics interface for the 0 domain, which is the infinite void. And so the surrounding domain, let's call it a void, and no extra boundary conditions are applied. We have a single coupling here, electric field coupling. So the frequency domain, the finite line model, is coupled to the boundary elements method here. That's how it's set up. And then it will create a so-called grid dataset. And here we can, at the post-processing part, you can control how big your control volume should be around your domain. So it will affect where you can plot the results. So here we have the Z. This is the vertical displacement. The maximum is 1.2 meters. So we can investigate the radiation pattern 1.2 meters. But you can override this and you can calculate any distances. So let's put this on to the graphics window and plot this. And so we are using this grid dataset, which is the boundary element methods solution. And we can plot the results far from our antenna. So we can calculate the far field pattern. So this is how it looks like wise. And if you want, you can see this is the surrounding box. If you want, you can create a bigger one or a smaller one depending on your needs. So you can plot the results far from your near field solutions. So that's technically a boundary element method in a few clicks. That's how it looks like. And if we go back to our presentation slides, so we have the second demo here, which is the LIDAR application. So we are using different physics interface. So we are using the geometrical optics for detecting obstacles in front of our radars and LIDARs. So let's jump into that model and investigate it further. So go back and open up that one. Ray, where is it? And LIDAR. I see it. Okay, let's open up this one. Okay, so as you can see here, so we have a geometrical optics physics interface. And from the domain selection, yeah, it's totally empty since we don't need those. We need only surfaces. So it's super easy to select. So we have groupings for the walls. So we have grouped together. And here we can set up different boundary conditions, how the rays should behave when they hit these obstacles like the car body, the buildings, and so on. So we can set up the absorption coefficient based on those, how the human body should behave, and other surfaces. Then we have the sources, one source in the front. So this is one sensor here at the front of the car. And we can set up the ray direction. It's conical. You can set up the axis of the cone, and you can set up initial phase if you wish. And currently the source power is defined here. And the same goes for the other sensors: front left, front right, right, and left. And we have one at the back. So these are the sources, and we have the detectors at the front. And here we have a deposited ray power, so we can calculate how much power it's back to this detector. So we have the same detectors in the front right, left, and the rear. And here the condition is always a freeze. So when the rays hit these detectors, they will freeze to those surfaces. Okay, so technically these are the conditions. So we have set up the walls, the sources, detectors, and we have the limits. So it will terminate if they hit those walls. So there won't be any further reflections. So this is the mesh, and we have only a surface mesh. So we don't need very detailed and complex 3D meshes. It's unnecessary for this ray optics, geometrical optics application. So it's super easy because we need to create only surface meshes here. And from the study nodes, so we have a ray tracing study setup here. And you can specify the length unit in, let's say, meters, or you can specify time steps where you want and when you want to terminate the solution. So here a length 20 meters is set up. So it will calculate until the rays reach 20 meters maximum. So that's it. So that's how the solution is set up here. And from the results, we can go and plot some trajectories for different time slots. And then we can plot what the detectors have seen during our simulation. So these are the ray trajectories at one dedicated time step. And then what's most important for us, then we can go to plot what the detectors have seen here. Okay, so here we have different curves. For one, the blue one goes for the front detector, the green one goes for the front left detector, and the red one for the front right detector. And we can see that so when the power goes to 1, so that means that it hits something. So the front, this is the green one, so the green is the front left, so it detected some obstacles at close to 2 meters. So that's the human body standing in front of the car at 2 meters, and there are some other obstacles at 6 and 7.5 meters. so the corner and the other car that is detected with the front, and we can set up the right detector as seen. And we can investigate all the other detectors and whether they have the right distance. We have detected the right distance or not. Okay, so we have the same setup here. So for optically large simulations like LIDAR, for example, to set up sensors, sources and detectors, geometrical optic, that's another physics interface, that's the most appropriate one. And you don't need to create any volume meshes or surface meshes. Based on the physics interfaces, based on the wavelength and the geometrical size, you can have different solutions, different physics interfaces. So not just an RF, also ray optics that also comes in place and comes in play where you can use for detection. And that was our other example, this LIDAR detection. So here in the application library, you can find a lot more examples. There are in some more than 800 examples. So you can find a lot for antennas, for filters, and for other multi-physics applications, not just for single physics applications. And you can find simulation applications in the library also, so you can test. Here you can see some of those applications. As you can see, they have a much simpler user interface. So you can distribute this to others, to colleagues, to customers, and they can investigate different parameters, how the results are affected by those. If you want to test for gratings, for directivities, and different applications. And then you can copy those applications to a dedicated ComSource server, so you can host them there. And anyone who has the address of those ComSource servers, he or she can access and can launch those applications and test different scenarios there. You can control different groups who have access to which part of the applications. So you as an administrator have a full control over the applications, and you don't need to send them by emails. You can just copy those to the ComSource server and anyone can access and wherever he or she is, so it's not tied to any computer.